Hi, kids. All right, here's my beautiful picture. Remember, I did minor in art. So I have a container. It's full of gas molecules. Gas molecules are moving around. Okay. Remember, okay, the average kinetic energy, okay, of any one of those gas molecules is equal to 3/2 the constant, Boltzmann constant, times temperature, and the temperature has to be in Kelvin. Okay. Um, So if this is an oxygen molecule and this is a hydrogen molecule and this is a nitrogen molecule, that as long as they're all at the same temperature, okay, the average kinetic energy for all these molecules is the same. Okay, even if they're all the same, if they're all oxygen, again, the average for the overall average is going to be the same. Okay, um, and again, it depends on temperature. Does this mean, though, that every single one of the gas molecules is moving the same speed? Of course not. Okay. Some of the gas molecules are going to be moving fast. Some of the gas molecules are going to be moving slow. So if I was to make a graph of this where I had the number of molecules versus the speed. So let's say in my container is only oxygen, and have this at 300 Kelvin. I would get a graph that looks something like this. Okay, if this was, let's say, this is oxygen at 300 Kelvin. Okay, on average, the kinetic energy of every molecule is the same. Okay, because they're all at the same temperature. In reality, okay, they're not all moving the same speed. Most of them are going to be right at around that average, but some are going to be moving faster, some are going to be moving slower. Okay, well, let's say I want to figure out what is a typical speed that those molecules are moving at. Well, if I wanted to figure out a typical speed, I have a formula for kinetic energy that involves speed, which is 1/2 mv squared. And then really this would be average squared equals 3/2 kT. Do you see how I could solve for V? So my 1/2 goes away, so I would end up with V equals, and again, 3 kT over m. And here's where you got to be careful. This is the mass of a single molecule. This temperature is in Kelvin. Okay, and then the K is Boltzmann's constant. And this is called RMS speed, for root mean squared, and it's a statistical thing. It's really where you're taking the square root of the average. Do you see what I'm saying? So it's called RMS speed, but as far as like what that actually means, the average would actually be here. The RMS speed is right here. Okay, it's right around there. So again, why do we worry about RMS speed? Because it's a really easy speed to find, and it's a pretty typical speed for the thing. So if you had oxygen and you at 300 Kelvin, you would have to figure out the mass of a single molecule. Remember, to do that, you would say, well, O2 is 32 grams per mole. And then you would have to say, well, I want to convert that to kilograms, because remember, this mass has to be in kilograms. So then you would say, well, I have 1 kilogram, I have 1,000 grams. And then you say, well, I have 1 mole is 6.02 times 10 to the 23rd molecules. And then that would tell you the mass in kilograms for a single O2 oxygen molecule. Okay, hopefully that makes sense. And then again, this is just telling you a likely speed. It's not telling you, the speed of every one. It's just the likely speed. Some are going to be way higher, some are going to be slower. Okay. One application of this is to explain why, for example, the Earth has an atmosphere where the moon doesn't have an atmosphere. Now to do this, now this was the thermodynamic stuff. I'm going to do a short little review over escape speed, which is not stuff you need to know for your test, but you'll need to know it because it's going to help us explain what's going on. So imagine you have the Earth, so we're talking about escape speed. So here's the Earth, and here is your little rocket that wants to escape the Earth. Okay, well, if it wants to escape the Earth, it has to be moving, and then as it moves away from the Earth, it's going to slow down, slow down, slow down, slow down, slow down. And if you gave it the perfect amount of speed just to barely escape the Earth, once it does escape, it would not be moving at all. So, all right, here's my picture, because remember in physics, we draw a picture first, and then we use our picture to write down our equation. Well, at this point, what type of energy do I have? Well, I have potential energy, because remember, if we are talking universal, the only place universally where you have no potential energy is where you have no force of gravity, which is where when you are infinitely away. So here I'm not infinitely away, so I have some potential. I have kinetic. Here I'm infinitely far away because I've escaped the Earth, so I have no potential, and I'm not moving, so then this is 0. And you might think, well, that's weird, but remember, and if you look on your equation sheet, you'll see it. It's negative GMM over R. That's the universal one. Plus 1/2 mv squared equals 0. And our m's would go away. And then if you look, you could say, well, v is going to be the square root of 2gm over r. So g is that gravitational constant, m would be the mass in this case of the Earth, and then r would be how far away I'm starting from the Earth. Okay, and in your packet, let me just look it up because I got my packet here. In your packet, it says for the Earth, the escape speed is for Earth, it is 11200 meters per second, and then for the Moon, it was 2370 meters per second. So here's the deal, okay? On the Earth, okay, if you think about this graph, now O2 is going to be all different temperatures, but they do this on page 17 in your packet. But even if you have a really big number here, like 1500 Kelvin, that oxygen molecules, when you're way over here, are never going to be going this fast, which means oxygen molecules are never going to escape the Earth's atmosphere. But guess what? If you were to do like helium, helium would escape the Earth's atmosphere, which is why you don't find helium in the Earth's atmosphere, or hydrogen. Well, the Moon, okay, oxygen is going to be moving faster than the escape speed for the Moon, so oxygen molecules over time are going to escape the Moon. So there you go. Hopefully that makes sense. Remember, this is the key part for thermodynamics, but this is that cool application. Yeah. Bye, kids.